Hello, you are host now. Mr. Omar, you are host now. You can share the screen. You can check.
Yeah. Can you see my screen now?
Yeah, I can see your screen. Yes.
Okay.
So again, I will make you the host because Nimesh will come.
And you can hear me, everything is fine, am I right?
Yeah, I can see the screen and
My voice is clear?
yeah, voice is clear. All is just see the moving of the screen, moving the PPT.
Sure.
Yeah, it is moving. Perfect.
Okay.
Mr. Omar, I will be again host for some time. Hello.
Yes, I can hear you.
Yeah. Mr. Omar, again, I am making the host myself because Nimesh will join for the presentation for 5 minutes as a speaker. Then again, he
Okay.
will host.
Okay, so shall I stop sharing now?
Yeah, you can stop the sharing.
Okay.
Mr. Nimesh Noor, hello.
Good afternoon, Mr. Omar. How are you?
Good afternoon, Mr. Nimish.
Yeah, now I will make Nimesh for his presentation after some time. Then again, Dr. Krishnan will come, will introduce you, and we'll start the main lecture.
Okay, great.
Okay. We wait for another 5 minutes, and I'll just join you in about 5 minutes or so.
No problem.
That's fine.
Yeah, now you are the host, Mr. Nimesh. You are the host now.
Yeah, Omar, good afternoon.
Good afternoon. Good afternoon. Hello, Dr. Krishna. How are you doing? Yeah, thank you.
How are you?
Alhamdulillah, everything is fine. Thank you very much. Thanks for having me again here in this.
So
great
you are at home today?
Yes, I'm at home.
Oh.
Yeah.
So we will start in another 5-10 minutes.
Yeah.
That's
Yeah, Nimesh has also joined.
Good afternoon.
Hello, Mr. Nimish. How are you doing?
Good. How are you?
Thank you very much. Everything is fine.
Great to have you back here.
It's my pleasure.
This is the 29th episode, yeah, Dr. Krishnan?
Yeah, Nimesh.
I said this is 29th episode, and I think now the chat is also working this time. We'll just try.
Yeah. Ah, okay. Just try that. Yeah, it's working.
Let's see if the participants can also message or not. So I requested people to just share a little hi, hello, or where they are from on the chat. It will be nice to know.
But for me, it shows only host and panelist.
Okay, so there is a drop below that. So I think if you look at the drop down, it shows everyone.
नहीं है, मेरा इसमें नहीं दिख रहा है.
Okay, so I think maybe it's still not activated.
Not activated.
Sachin, you may need to talk to the Zoom people and get this activated immediately, huh? We'll get Abhishek and others to kind of get it done. I think people are raising hands. That means it's not yet active.
Tomer, how are things in Sabik?
Everything is fine.
Shutdowns are happening now or over?
Well, it's a complex, so I mean, shutdowns never stop. Huh?
Yeah, because in India, lots and lots of shutdowns are happening in September, October time.
Yeah.
It's almost getting over here.
Yesterday, I have forwarded the message to NPCL also.
Okay.
And I think NPCL, Mr. Astana has been kind enough to forward it internally to all.
Okay.
So I expect a good amount of people to join from there as well.
And
Great.
just 56 today morning is increased. So maybe of NTPC people.
Yeah.
So Nimesh, you are host now. And I just share the Zoom person number, Abhinav, to you.
Okay, so it's 5 o'clock. Should we wait for another 5 minutes, Mr. Omar, for people to join in?
That's fine for me. That's fine.
Yeah. Dear
That's fine.
participants, you have joined in early. I just request you to wait for another 5 minutes, and then we can start the proceedings for the day. In the meantime, Dr. Krishnan, would you like to introduce IIW? So it's 5 o'clock. We can start with the introduction of IIW.
Do we have that PPT, Nimesh?
I'll check. Yeah, we do. I will share that PPT if you want.
Yeah.
We'll just go YouTube live as well in the meantime, so that okay. Sachin, I hope you're recording the session, yeah? Yep, recording is on. All right, so we'll do one thing. I'll quickly share the presentation for the IIW Mumbai branch. Dr. Krishnan, if you would like to take it up.
Yeah.
Please go ahead.
Yeah. So good evening, everyone. So welcome you all to the next episode of the Weld Tech Talk. And today we have a very interesting session on P91 by Mr. Omar or Sabik. So before we get into the Tech Talk, brief regarding Indian Institute of Welding, especially Mumbai branch. Next, Nimesh. So we all know that it's a non-profit organization and with the head office in Calcutta. And we are having more than 4,500 members. And Indian Institute of Welding is also part of the International Institute of Welding. So the basic objective is to assist human resource development in welding in India, and to foster R&D in welding, the technology diffusion to industry and the individuals. So a lot of activities are being done to promote health and safety in welding, and we also ensure that international standards of quality are being deployed in the Indian fabrication industry. So we at IW conduct a lot of technical meetings, workshops, industry-oriented training programs at various branch levels. So as far as Mumbai branch is concerned, we conduct a lot of workshops, and this Weld Tech Talk is a perfect example where we get speakers all across the globe, and even the participants are from various countries. We get even participants from almost 25 to 30 countries to attend this. And we also run a lot of refreshing courses related to welding and quality. And the IIW also publishes Indian Welding Journal, which is done quarterly in collaboration with American Welding Society. Image next. IW also does a lot of welding certifications under A&B for examination and qualification of welding personnel like International Welding Engineer, welding technologist, International Welding Specialist, welding practitioner. And those who are interested can be in touch with us so that we can guide you to the right person at the head office. And we also have association with various national skill development authorities and programs like Automotive Sector Skill Council, Capital Goods Sector Council, Indian Iron and Steel Sector Council. So as I already told, we have Indian Welding Journal, and we conduct a lot of branch and national level technical programs and seminars. So in Jan, we are going to have an International Welding Conference. This time it is being done in Bangalore.
Along with IMTEX.
Yeah, it's going to be along with IMTEX with an exhibition. And at the branch level, we are in November, we are going to have a competition for the best welders. And IW also conducts at national level the best welding engineer competition, which will be rolled out soon. So we request all of you to participate, those who are interested. So all of you, those who are not members, are welcome. You can be member of the IW. There are certain criteria to be it, and the membership has been made online now. So being a member, you have a lot of advantages that you can be even part of all these initiatives which IW is offering. So we have a variety of memberships like associate member, associate professional member, and even student membership is available, and you can even be a life member. So those who are interested, please be in touch with us.
Also, just to highlight, if you come from a university or an institute, you can connect with us for a student chapter where your students can take advantage of many of these programs on welding awareness. And we do a one-to-one connect, and we also explore industrial exhibitions and things like that for them, where the students can go to industries, see what the work is, or that a welding engineer or a welder does, and they get a lot of exposure. So if you are a part of an institute or a university, please get in touch with us for a student chapter to start a student chapter within your institute.
So these are details of the various membership fees.
And the membership is quite light, and I believe that it is now online. So you can go to the IIW India webpage and you can fill up the form for there itself. And we really do encourage people to become part and support this initiative. Right. For any queries, you can note down this email ID, follow us on LinkedIn and Facebook, and be in touch with us. Right?
Yeah.
Thank you, Dr. Krishnan. I'll stop share here.
Yeah.
And it's 5:08. I'll take another 3 to 5 minutes to introduce SigmaWeld. Yeah, and then we got more than 110 people, Mr. Omar. So we'll start off in the next 5 minutes. The stage will be all yours. So just briefly and quickly, I'll try to introduce our company. Give me a second to share the screen. Is this visible?
Yes.
Yes, Nimesh.
All right.
Yes,
So
yes.
very quickly, a little bit about me. My name is Nimesh Chenoy. I'm the Director Technical at SigmaWeld. I have a double degree from Royal Melbourne Institute of Technology at Australia, and I have done my PGDM in Family Managed Business from SPJN Institute of Management and Research in India. I have 20 plus years of application engineering in welding and induction heating. I have authored and presented more than 100 technical papers on welding, induction heating, and IoT for Industry 4.0 at both national and international conferences. Been awarded the best technical paper at the National Welding Meet held in Cochin, and our paper on aerospace welding selected for the Welding in the World magazine. I'm also the honorary secretary of the Association of Welding Product Manufacturers in India. I've recently also become a member of the BIS committee, which is responsible for electric welding equipment, which is an ETD 21. I also am the industrial corporate member representative at the Central Council for Indian Institute of Welding and on the core committee of welding for CII. I'm very happy to say that Weld Tech Talk is something that Dr. Krishnan and we started back in 2020 during COVID days. And over the last 29 months, it's taken a very good shape. And I'm very happy that many people are taking benefits of this talk. And we have excellent speakers like Mr. Omar, who've been able to, help us contribute more to the knowledge sharing for everyone. Quick journey about our company, Electronic Devices. It's been 49 years, established in 1974. We started with dielectric preheaters as an import substitute for India. Soon we got into induction heating equipments. We moved to induction sealing, which is the first time it was done in India in 89. With 91, we did a JV with an Italian company to do heat treatment of the Agni missiles. We made India's first 2000 kilowatt induction heater. Today, we fully own that company and operate it out of Mumbai, India. We established our R&D as a professional body in 2000. And I'm very happy to say that this R&D department is now a Government of India Department of Science and Industrial Research approved laboratory. In 2010, we expanded our works from Mumbai to Gujarat, Umargaon. And 2007, we started our welding inverter product line, which is 100% made in India. Starts with arc, TIG, MIG, submerged arc, and the whole works. We do even automation there. 2012, we moved from a private limited company to a partnership company. Today, I'm proud to say we hold more than 4 patents. 2 or more are under defense. So it'll be about 6 patents by the end of the year. We also hold the National Technology Award for MSME this year for science and technology. Electronic Devices, 49 years of experience, more than 287 dedicated employees, 80 plus countries we are exporting to, and more than 10,000 happy customers globally. Very quickly, contributions that SigmaWeld has made. So the full range of welding inverters and automation solutions have been used in Chandrayaan 1 and 2 for the fuel booster welding. Gaganyaan semi-cryo engine heat treatment procedures been developed by us. The six nuclear submarines guarding India's waters, the titanium bundles welding, and the end pin heat treatment. We've contributed to more than 100 kilometers of aluminum foot overbridge welded for defense. Safe and locks that are used largely in India and the banks by Godrej, 100% welded on SigmaWeld, nuclear end shields for NPCIL, and a lot of work done for the atomic research in the Indira Gandhi Center for Atomic Research. We have more than 10,000 equipments working with over 1,000 MSMEs across India and helping them build the nation better and faster. These are a few of the awards that we got. Pride of the Nation, the National Technology Award this year, the Best Welded Present, and the Make in India Award for a couple of products that we made. So with this, I would like to hand over again to Dr. Krishnan. Thank you very much. And you can please introduce our speaker for the day.
Yeah, thanks, Nimesh, for the brief introduction regarding Sigma. So coming on to today's session, our distinguished speaker, Mr. Omar Alafi, is a senior inspection engineer with over 15 years of industrial experience within oil, gas, and petrochemical industries. His specialization is widely covering ASME B31.1 piping, pipeline design, construction, operation, inspection, pigging, maintenance, repair and integrity assessment, process equipment, reliability management, and he has been conversant with various codes and standards like ASME, the EN codes, the EN standards. So he is presently working with SABI Group, and he has a very rich experience in the oil and gas field. Basically, he is a mechanical engineering graduate, and he is certified in CWI AWS, API 570, API 510, API 577, and API 571. And he has delivered many technical talks and courses in Middle East region, and he has been kind enough to give his second talk as part of this Weld Tech series. With this, I request Mr. Omar to take over the session.
Thank you, Dr. Krishnan. I'm not sure, can I share my screen now?
Yes, Mr. Omar, you are now the host.
Okay.
Yes,
You can see my screen, right?
absolutely.
Yeah. Thank you very much. Thank you for the introduction, Dr. Krishnan. And before I start, I would like to thank you for this great knowledge share platform you created. You guys are amazing, and I feel proud being here with you again today for sharing this technical session. Our topic for today is about the best practice guidelines for welding and repair of P91 material. I'll start with the outlines, the topics we are going to cover: the development of P91 steel, metallurgical properties of P91 steel, physical properties related to welding, advantages of grade P91 over the conventional chromium moly steels, the preheat requirements, the filler materials we should use during welding, general welding requirements, the dissimilar with metal welding, post-weld cooling. This is post-weld cooling, not heating, and we'll speak more about this. The post-weld heat treatment guidelines, weld repair of P91 material, and we'll share 3 case studies about P91 material. The development of steel as introduction. This grade of P91 was developed by Oak Ridge National Laboratory in Tennessee, USA. And the extensive studies and the result of extensive studies done for this material attracted the attention of designers because of its higher strength and creep resistance, and the lesser weight required for manufacturing pipes and fittings. So the first use of this material was in 1983. This is when P91 material gained its acceptance through the code case 1943 in ASME section 1. This is the timeline for developing the material and the work studies done for this material, and the code cases for accepting P91 material in ASME section 1. The first code case was, as I said, in 1983. And after that, many case studies or code cases accepted for forging and casting as well. The metallurgical properties. So P91 is a deep hardening steel. And what do we mean by that? If you look at the right bottom, the chart on the right bottom, you'll see that a test done by Germany end quench test for 2 materials, P22 material and P91 material, both have almost the same carbon content, but the hardenability of P91 is much higher than P22 material. This is in part because of the martensitic formation during cooling. That martensitic structure in P91 will give higher strength and higher hardness in the steel. It's very important to notice that the AC1, or the lower transformation temperature of AC1, is a function of minimum and maximum nickel and manganese content in the material. So the tempering of the welding of the weld metal is done close to this temperature, the AC1 temperature, and the content of nickel and manganese can lower this transformation temperature and can bring our PWHT temperature above this critical line. It should be noted that we shall never exceed this line during our heat treatment. We'll speak more about this, but this graph on the left side shows how nickel and manganese content can lower the transformation temperature, or AC1 temperature. In ASME, we have a limit of 1% for both nickel and manganese in the material, in order to not to exceed this temperature during PWHT. This table shows the chemical composition of different grade of 9 chrome 1 moly steels in different specifications and code cases. And we'll go to martensitic formation. As I said, what gives the strength for this material is the martensitic transformation upon cooling. So during cooling from austenization temperature to room temperature, the martensite structure will form upon cooling, and that structure is what is required in P91 material. So P91 material is not another low alloy steel. It's a different grade and should be treated as such. So the tempered martensite has a better creep resistance and a better creep rupture strength for this material. It is important, again, to be sure that tempering temperature does not exceed the lower transformation temperature AC1, which can affect the creep rupture strength of the material. This table shows the heat treatment for manufacturing different fittings and pipings, and forging as well in different specification, and minimum tempering temperatures required for these material. The physical properties, I will speak about two properties here: the coefficient of thermal expansion. In the coefficient of thermal expansion, we know that the higher the coefficient of thermal expansion, the higher the distortion susceptibility. In part because when you have a high thermal expansion, the possibility of expanding during welding is more, and that will create more stresses and make it susceptible to distort during welding. So as we see in the table, in the graph, P91 material has a lower thermal expansion coefficient than P22 and austenitic stainless steel. Whereas the other physical property is the thermal conductivity, and higher thermal conductivity is better in preventing distortion. And we see P91 is lesser than P22, but it's better than austenitic stainless steel 304H grade. So the advantages or the differences between P91 as compared to P22. It has superior performance at elevated temperature, higher strength, better creep resistance, lesser weight, and lower coefficient of thermal expansion. And in the photos below, we see the difference in weight and the difference in wall thickness. So you can save up to 65% of the weight when using P91 material. And the difference in wall thickness is around 50%. This is a big thing. So lesser weight meaning lesser or lower cost. So that's one of the things that attracted the designers for using this material. So this is very important during construction when you have lesser weight. This is lesser supports, lesser welding consumables. Everything is less, and it'll save cost. So for welding variables between P22 and P91, preheat for both is required. PWHT, yeah, sometimes for some thicknesses can be waived, but for P91, it is always required. So the normalizing and tempering after cold work, it is always required for P91. Post-bake or post-heating, it is recommended for P91. It is optional, especially when you use low hydrogen designation electrodes. It can be optional, and sometimes it is used for P22 as well. For post-weld cooling, it is not required in P22, but it is very important for P91 in order to achieve the martensitic structure in P91. The bead sequence is always required. We have to follow the bead sequence from the bevel side to the center of the bevel, and inner gas purging is always required, not only for the root pass but also the hot pass as well, and we'll speak about it in the upcoming slides. So preheat requirements. The risk here is the hydrogen-induced cracking. So this hydrogen-induced cracking is can be controlled by these factors: the stresses in the joint or the tensile restraints, the susceptible microstructure. We know that P91 has a microstructure that can be susceptible to hydrogen-induced cracking if improperly controlled. And these things, these 1 and 2, cannot be controlled by welding. What we can control by welding is the hydrogen diffusion in the thickness or in the steel. This hydrogen can be picked up from the liquids on the pipe, or the moisture in the atmosphere, or the filler material that can have hydrogen. So for these things, we should use low hydrogen designation electrodes, and we should keep our preheat temperature between 150 to 250. I would like to bring your attention here to a very important point, that preheat by torch is not allowed. It cannot control the preheat temperature. It should be done using ceramic fiber blanket, and it should be monitored by thermocouple according to the illustration shown here. So the distance between the thermocouple and the edge of the weld is 50, and an element to the weld is 100 mm. This is to give proper access to the welder. And of course, if you have access from the ID, thermocouples should be installed from inside as well. Filler materials. For filler materials, I have 3 points here. The first one is the matching filler wear. So we should always use matching filler wear, but I know that this is not always possible. Sometimes we might have dissimilar weld joints. We all know that dissimilar weld joints are not recommended, but in many cases they cannot be avoided. So for welding P91 to another low alloy steel, we should use undermatching filler wire for the weld joint. We should butter it. We'll see this how can we do this later on, but we should butter the P91 with undermatching filler wire, ATS B8 or a similar filler. And when it is joined to an austenitic stainless steel, nickel-based filler wire can be used for the similar weld joint. The table here shows what type of filler wire should be used when you have the similar weld joint. For the chemical composition of the filler wire, I should bring your attention that the MTC should always be verified for each filler wire to be used in the welding. Most important elements, the phosphor and sulfur in the filler wire should be less than 0.01. I know sometimes you might find it 0.02 or 0.025, but it should be always limited to 0.01. These elements have, in addition to silicon, of course, have low melting point. So this low melting point during welding can create hot cracking. So it should be noted that phosphor and sulfur should not exceed 0.01%. The other two elements that should be monitored, as I said earlier, manganese and nickel. Manganese and nickel should be limited to 1%. If it's to be exceeded, if it's to be higher, this should be approved by the owner or the purchaser. Also for short circuit GMAW, the silicon limit should be 0.35 or higher. This is because if it is less, it will affect the wetting action of the filler wire and creates many problems of lack of wall fusion. This is a common issue, a common problem in GMAW short circuit, and it is addressed by ASME Section 9, where welders using this method be qualified not only by NDT, but by mechanical test. The interpass temperature. So an interpass, the purpose of interpass is to permit a reasonable welding productivity rate, but the temperature should be of a reasonable upper limit to prevent excessively slow cooling. So slow cooling here, as you see here, if you have slow cooling, it might intersect the alpha nose here, and you will not have a martensitic structure. So it should be high enough to have a proper cooling rate of the weld. The temperature, the interpass temperature also should be sufficiently low to prevent issues with hot cracking. So as I said, if it's too high, it can melt those elements like phosphorus or sulfur inside the steel and can create hot cracking if the content is too high. This is again a reminder that we should always verify the MTC and do PMI for the filler material. General welding requirements here, as I said, all SigmaWeld electrodes should be certified to H4 designation. The back purging of the shielded gas for GTAW is 100% welding grade argon. And the back purging shall be kept until at least the root pass and one hot pass have been deposited. So the maximum heat input also, this heat input should be 1.2 kg. This is why we restrict using small filler wire of 2.5 or 3.2 mm to the root to have or to reduce the heat input and reduce the width and the extent of the heat affected zone inside the base metal. The interruption, any interruption of the welding should be avoided until at least 10 mm weld metal or 25-30% of the groove thickness has been used. If this interruption is occurred, it should be tested. Preheat should be restored and maintained. And if there is any moisture or accumulated on the weld during the interruption, it is better to cut the weld and re-weld it again. For post-heating, as I said, is a good practice, especially if low hydrogen designation is not used for filler wire. And to reduce the risk of introducing defect for root pass, the filler wire should be limited to 2.5 mm. Okay. In this photo here, we see that during bend test, the sample failed the bend test using 4 mm filler wire size, and this is why we should limit welding the root pass to 2.5 mm filler wire. For the size of or the angle of the bevel, it should be 10 to 15 degree as shown here. So we'll see later on in the slides that how this angle can affect the service life of the weld joint. So the common practice we follow for 37 degree or so can adversely impact the service life of P91 material. And as I said, the bead sequence should be from the bevel to the center of the weld. This is for both weld repair and new bevel. For the similar weld joints, so for the similar weld joints, we see that one of the important things that we should do is the step bevel. So this step bevel is very important, not only in the similar weld, but also for thick components. We should also use this step bevel. The reason is that the susceptible area for having a crack is the heat affected zone. This is because the fine grain structure or the soft area that can have type 4 cracking in P91 material. So the location where the crack can initiate is within the heat affected zone. So if it's going to propagate, it will propagate through the heat affected zone. So the area here, this area here is the base metal, which has better creep resistance, so it will stop the propagation. But this distance from here to here should be at least 10 mm or higher. So we have common cases where the distance of the step bevel was less than 10 mm and the crack initiated. We can see in this photo how the crack propagated through this small step bevel of lesser than 10 mm, and the propagation stopped at the edge of the 10 mm bevel. So we can see this the effect of this step bevel, how it can prevent the propagation of the crack. This is recently mentioned in API 582 about having step bevel in the similar welds. API 582 Appendix F in 2023 edition. They have published a good practice for P91 material. And this is one of the requirements that should be followed when having a dissimilar weld. For joining P91 to low alloy steel, for example, P22 material, so the steps are as follows. We should better the weld with P22 filler material, and then do the PWHT as per grade 9 requirement, and then the weld joint will be welded using P22 filler wire. For stainless steel, the weld will be done using Inconel or NICR3 on the V shape prior to completing the butt weld joint, and then the buttering will be post-weld heat treated according to P91 practice, according to the practice for P91 material, and then complete the butt weld using the same filler wire without PWHT. So why we do this? Because as you see in the table, the lower temperature or the lower critical temperature or AC1 temperature for P22 or P11 can be lower than PWHT temperature for P91 material, and this can create a problem. We know that we should not exceed this this temperature. So this is one of the reasons why we should take care of welding P91 to a different grade, and this is why we use an undermatching filler wire for welding this dissimilar joint configuration. This is an example of poorly controlled welding during dissimilar welding. We see in this colored colored photo, the depth of the heat affected zone is almost 70 to 80% of the wall thickness of the tube. So this created a problem, and the crack initiated from there and resulted in a rupture in the joint. So this is due to high heat input during welding. So in such cases, we should consider the size of the welding consumable or the filler wire used, or we should have a skilled welder who can control the welding to avoid excessively slow rate or slow travel speed during welding to reduce the heat input. So increasing the heat input can result in high thickness extent of the heat affected zone. Post-weld cooling. So as we said, the martensitic formation will be done after we cool the weld. This post-weld cooling is not required for P11 or P22, only for P91 material. So the structure will transform to full martensite after cooling to ambient temperature. As we see here, this is the transformation temperature. So the MS is the start point for transformation to martensite, and the MF is the finish point for martensitic transformation. And it should be noted that MF just around 100 degrees Celsius. So in order to have or to ensure that we're having full martensitic structure in P91 material, the temperature should be brought down to below 100 degree or room ambient temperature. But I should emphasize here that this after cooling, it should be sent directly to PWHT. There should be no time between bringing the temperature down to ambient temperature and PWHT. The moment we reach to room temperature or ambient temperature, we should go directly for PWHT. In part because this can create stress corrosion cracking if it is exposed to moisture or exposed to sulfur species. And we can see here on this graph the difference between in creep resistance, the difference between two materials with post-cooling and without post-cooling. So the material with post-cooling shows that we have a better creep resistance. For PWHT, so why we are doing PWHT, it's not because of the base metal, it's the weld metal. So the as welded P91 material have a high hardness of 50 Rockwell C. So it has to be tempered. And as you see in this paragraph, the temperature of the as welded is here. This is the temperature of the untempered martensite. It's in the range of 400 to 450, whereas after heat treatment, it goes down to 250 to 300. So without tempering, as I said, it may be prone to stress corrosion cracking prior to PWHT, and the delay or omission of PWHT might result in intergranular cracking if exposed to moisture, and transgranular cracking if exposed to sulfur species. And intercritical heating between AC1 and AC3 promotes type V cracking or cracking in the heat affected zone. In here, I would like to say that we should have proper thermocouple distribution under the heating pads and from both sides, from OD side and from ID side as well. And all these points should be witnessed during PWHT. So this illustration is for PWHT and the distribution of thermocouple and heating element, and we can see that in this weld has resulted in cracking in the weld because the MN and NI element were not verified and resulted in type 4 cracking in the weld. So we should always verify the content of nickel and manganese prior to welding. So the PWHT procedure should be reviewed carefully. This temperature, AC1 temperature, should be calculated for a known composition. And the chart on the right side shows how the AC1 temperature can change with a different composition or content of as a function of nickel and manganese content in the steel. This is the minimum and maximum PWHT temperature according to ASME section 1 and ASME B31.1. For post-weld heat treatment, as I said before, the AC1 of the weld is not exceeded. This is very important. Why? Because it will not have a martensitic structure, will have a ferritic structure, a different structure in the steel that might be prone to cracking during service. And in premature failure in P91 material is most of the time attributed to improper PWHT. So it is a good practice to determine PWHT holding time and PWHT temperature on testing of the welding procedure qualification, and that welding procedure qualification should be strictly followed. So the type 4 cracking, I spoke about type 4 cracking. So the cracking of the weld joint is usually classified or categorized according to the position of the crack. So what do we mean by type 4 cracking? Type 1 and type 2 are within the weld metal, type 3 in the coarse grain area, and type 4 is in the soft or fine grain area, as shown here. This is the area. This is where the hardness sharply dropped down in this area, making it susceptible to cracking, or it will affect its creep strength and creep resistance during service. So these are the steps that should be verified and carefully monitored and cross-checked before, during the PWHT. We should have inspectors. We should not have or rely on the contractor who's doing the PWHT. The first thing, maybe not mentioned here, but I would like to say about the qualified vendors for PWHT. So it is very important to ensure that the vendor who's doing PWHT having the experience in heat treat or post-weld heat treating of P91 material. We are doing the heat treatment very close to the transformation temperature or AC1 temperature, and many factors can affect the accuracy of the post-weld heat treatment. If the temperature goes slightly above the specified temperature, we might exceed the lower critical temperature or AC1 temperature, and resulting in cracks during service. So the points are that the insulation, the pads must be properly sized and without gaps and without overlapping. At least one thermocouple installed under each stress relief heating pad. A single control thermocouple should not control multiple heaters, yes, and multiple control zones for joints with dissimilar thickness transition. This is very important when you have dissimilar thickness between the two sides of the weld. We should have multiple thermocouple for controlling or monitoring the temperature in there. And the thermocouple location should be from OD as well as ID. The soak band, the heat band, the thermal gradient band should be calculated, marked at site, and witnessed. This is very important for any inspector or inspection engineer involved in P91. These steps are very important to be witnessed. And as you see here, the gradient, the temperature gradient of the heating band, as shown in this IR image, we have different temperatures. So the location of the thermocouple should be under the highest expected temperature, and it should be insulated as shown here. So these are the charts for soak band, heat band, and gradient control band. As I said, these should be calculated and marked at site and shown in the PWHT procedure for this material. So post-weld heat treatment for dissimilar welding. As I said earlier, the welding for dissimilar weld is sometimes used using or done using different grade, not non-matching filler wire, like under-matching filler wire or nickel-based filler wire. So the PWHT, when P91 is joined to austenitic stainless steel, is done after the first battering, and when joined to P22 material is also done after the first battering layer, according to this PWHT temperature shown here. These are the temperatures for dissimilar weld joints. For weld repair of grade P91 steel, as I said, this step bevel configuration is recommended not only for weld repair, but also for a new weld as well. So when we have a defect in the weld, this D is the depth of the excavation. We can excavate and ensure that the defect is fully removed by dipenetrant test. And after that, we should ensure that the corners of the bevel is rounded to avoid lack of fusion. And the angle, as I said, should be 10 degree to 15 degree. This angle, if you see this chart here, it shows the comparison between different angles, and it shows that with 10 degree bevel angle, the time to failure, so the joints were tested with different bevel angles, the time to failure was double the time required for 25 or 35 degree bevel. So this is the first one, and the second point is regarding the width of the step bevel. It should be at least 10 mm. It should not be less 10 mm. According to the recent publication of API 582, it should be 13 mm or half inch. And the bead sequence or the filling should be from the bevel side to the center of the weld. So the first pass or the root pass should be done using 2.5 mm. Also, the hot pass it can be used. It can be done using 3.2 mm, but the best practice or the good, it is much better to use the same filler wire size. And for fill passes, the diameter of the electrode shall be restricted to 4 mm, no higher than 4 mm. So in nickel, but for nickel base filler metals, it is very difficult to do the welding using 2.5. So 3.2 mm diameter electrode can be used, but we should ensure that skilled welders having good experience in P91 welding are deployed for this job, and the overlap between the beads should be at least 50%, and waving is not allowed for reasons related to high heat input and thicker heat affected zone in the base metal, which can make the weld or the heat affected zone susceptible to cracking during service. The first case study is related to failure due to improper PWHT. This has happened in superheater tube. The tube failure occurred over a period of 2 years after 26,000 hours. The material was P91 tubing of 1.68 inch or 42 mm OD and 7.4 mm thickness. So we see the fish mouth cracking in the tubes, and the hardness here was much lower than the hardness away from the weld. So this is a sign we had a soft grain, and this is an evidence that the AC1 was exceeded during the weld. So as I said, the hardness in the section away from the weld from the failure side averaged between 188 to 220 Vickers hardness, but it was around 159 in the area of failure. So the conclusion is the failure, the tubes were characterized as long-term overheating, possibly linked to oxide scale exfoliation, and the microstructure hardness of the area close to the weld provides an evidence that the weld did not receive proper PWHD. The second case is related to improper design. So that was a poor design, weld OLED, welded to 18-inch pipe, and the crack was in the 12 o'clock position. Cracking was to be associated with extensive creep cavitation in the coarse grain and fine grain area, as we'll see in the photos. And it was about halfway through the wall. So the cracking was attributed to type 4 creep damage in the inherently soft fine-grained region of the heat-affected zone, and it occurred after 18,000 hours. So this also suggests that this weld might be highly stressed in addition to the stress concentration induced by the geometry. So weld OLED fitting was eventually replaced with a forged T piece. As we see here, the creep voids in the microstructure, and the weld OLED was concluded to be prone to early type 4 cracking because of the high stress concentration produced in the weld, and weld OLED should be avoided in the new construction. Forged T should be used. The last point, the last case study is related to fabrication error. So the location, as you see here, at the edge of the weld, pipe welded to a nozzle. The nozzle is P11 material, and the main steam pipe is or the nozzle is P11, and the main pipe is P91 material. The crack was in between the weld and the nozzle. The location was at the dissimilar weld metal between the piping and the inlet nozzle, the P11 or grade 9 material. The failure occurred after 4,000 hours of operation, and the crack was located in the outer part of the heat-affected zone on the nozzle side. So, as we see here, there was missing weld beads. So this has contributed to the early failure in this weld configuration. So P91 material, it was concluded that P91 material might be vulnerable to strain localization damage due to the mismatch in the creep properties and any additional geometrical stresses concentration. And we should always have a good inspection program for all dissimilar weld joints, and in particular the P91 dissimilar joints having P91 material. By this, I conclude my talk for today, and thank you everyone for attending. Do we have any questions?
Yeah, Omar, there are a few questions in the Q&A session. You can just click on that.
Yeah, the first question is for welding P91 to P11. Is it recommended? As I said in my presentation, the similar welds should be avoided. But in case it is not avoided, we should ensure that the P91 is battered with P11 filler wire, heat treated to according to P91 material, and after that welded with P11 material and heat treated to the P11 material or the temperatures specified for P11 material.
Omar, there will be a challenge here if you try to join P91 to P11 directly. Okay, so the PWC temperature for P91 is going to be quite high.
Yes.
So getting P11 material of that PWC temperature simulated is a big challenge. So another way to handle this is by providing another spool of say P22 in between.
Yes, or transition piece. Yes, this is one of the points to avoid such configuration, to have a transition piece of P22 material between the P91 and P11. The second question is what is the reason for controlling nickel and manganese to 1%? As I said in my presentation, nickel and manganese can affect can lower the temperature, the AC1 temperature, which is the lower transformation temperature, which we should not exceed during PWHT. So higher content can lower this temperature, and during PWHT we can exceed this temperature, resulting in improper microstructure for the weld, making it susceptible to crack. 10-degree bevel is normally used for narrow gap welding, but SigmaWeld or other welding process. What is the joint bevel angle? No, for P91, as I said, for P91, the bevel should be 10 to 15 degrees Celsius, 10 to 15 degrees. So it was experimentally tested that this 10 degree is the best angle for the bevel in P91 material, and we should not go with the common practice for 37 degrees as it may reduce the service life. How many thermocouples are required during as much as possible? I would say that under each heat pad we should have a thermocouple from both sides, OD as well as ID. And how design restraint weld joint play a role in weld cracking rather than welding? So the design restraint, I mean, you will have these excessive stresses when you have or a dissimilar thickness between the welds. So this can play a role in weld cracking. So this also should be avoided. But when it cannot be avoided, this has to be controlled by welding, and ensure that Okay. Yeah. Wait a moment. Anytime. Sorry, it closed. What are? Shall I start? What are the reasons for controlling nickel and manganese? 10-3. Post heat. What is the difference between post heat and heat treatment? Post heat is post baking, but PWHT is post weld heat treatment. So post baking is to release the hydrogen inside the metal. But PWHT is meant for tempering the weld bead, the as welded, and
so
the hardness of
in terms of P91 or other chrome moly variants, if you stop welding in between, you may have to take it up to DST or post heat, which is about 300 to 400 degrees depending on thickness and material. And in PWHT, you go all the way up to 560 or 600 degrees plus, and then you have to temper or normalize the steel. So these are two different processes. Post heat is only meant to take care of the hydrogen diffusion and DST in between the heating cycles or welding cycles. PWHT happens at the end of your entire welding when it's completed, just to add a fair bit to it.
Yes. Can we weld the similar weld without battering? No, battering is required, but the issue with battering here that it's difficult for testing. For example, we cannot rely on PAUT for testing the weld batter. So this is one of the common issues. But battering is required when joining austenitic stainless steel to P91 material. What is the cost comparison between P91, P12, and P22? I'm not sure about. Are you talking about the cost or the cost saving? So there will be a cost saving at least no less than 50% when using P91. So it's not only about the price of P91 as compared to P92 or P22 material, but also the saving in the weight of the piping components, the fittings, the supports. Everything will be less, and you will have you will save a lot of money during the erection and construction of P91 material. Why interruption of the welding should be avoided at least at 10 mm? At least at 10 mm. I'm not sure why, but interruption as a concept it should be avoided for reasons I mentioned earlier, that interruption can result in cracking if the weld is exposed to moisture or to sulfur species during welding.
And not only that, if you don't put sufficient weld, it won't be having enough strength to hold. So naturally, there is a possibility because your hardness will be quite high for this weld, and if it's not sufficient to hold that, say pipe to pipe, there is a possibility that it might crack. So sort of restraint crack.
Yes. Is it advisable to perform PWHT with a slow cooling rate during performing PWHT? PWHT heating and cooling rate should be slow. Should be limited to 100 degree up to 400 degrees Celsius, and after that it should be reduced to 55 degree per hour. So what is the PWHT for SS316? Step cooling is mandatory for P91 welds or post cooling. I'm not sure about step cooling or post cooling.
No, by step cooling, I think
they mean temper embrittlement.
Yeah, correct. Which is not the general case with P91.
No.
Yeah.
It's not susceptible to timber embrittlement. Why many users not allowing casting for P91 material, always asking for forged valve irrespective of the size? Kindly explain. I'm sorry, I don't have any experience with any casting grades, but all I know that we have a code case for casting material. We always use the forged valve in P91. What are the actions should be taken? Power failure during PWHT. Ramesh, what are the actions should be taken? I spoke about the actions that we should verify and cross-check during PWHT, that the heating pads should have no gaps, there should be no overlapping, the thermocouples should be the location should be under the highest expected temperature under the heating pad. Under each heating pad, we should have thermocouple from both sides, from inside as well as outside. The heat band, the soak band, and the control gradient band should be calculated, and all these activities should be witnessed by inspectors and inspection engineer. Is post heating required for GTAW base metal tube? Post heating in P91 is optional. It's okay. You can do. But when you have low hydrogen electrodes, you can waive it. The most important thing in P91 is not the post heating or the post baking, but the post weld cooling. Post completion of P91 welding, it is recommended to do PWHT in continuation to post heating, but in avoidable condition, we do post heating and cooling the weld to room temperature. Suggest the standard cycle to be followed. The standard cycle for cooling is to cool it in still air to room temperature or to below 100 degrees Celsius. So we remove the heating pads, the insulation, we remove everything, we let it cool in still air. Grade P91 material required simulation heat treatment, including PWHT. Yes. Simulation heat treatment is a good practice to be done. So and also if you can have this simulated in the WPS qualification itself, that's fine. So you can have a simulated in heat treatment during the WPS qualification. How much should be the minimum battering thickness for P91 to P11 or P22? So it is only one layer. يعني 3 mm battering is sufficient for dissimilar welds. But as I said, يعني P91 to P22 is a difficult dissimilar weld configuration, or it can be worse if welded to carbon steel. So this should be avoided. But one layer of welding is enough, heat treated according to P91 requirement, and then welding using the low alloy steel filler wire. ASME Division 8, given the holding temperature is 705 degrees. To have higher holding temperature, what is the suggestion? So higher holding, as long as you are below the critical temperature for it is fine, but it can result in a softening grain areas in the heat affected zone. So we should follow the specified holding time in ASME. So I know some people that they do the holding time 2 hours or more, or 5 hours at least, but we should follow the ASME standard. Where to get P91? What is the cooling grade for? Let's look at this. What is the minimum? We do post heating. We do post heating at 300 degree. Post heating is fine. 300 degree is fine, but again, you can wave it. How the part going to start martensitic transformation after cooling? So after post heating, you should remove everything, the heating pads and everything, and let it cool in still air. Below 200, it will start transformation to martensitic, and it will finish or it will complete the transformation below 100 degrees Celsius. As my understand, post-weld cooling treatment is playing a vital role. Yeah, this is, as I said, the most important thing, or the main difference in welding between P91 and P22. What is the shelf life for SigmaWeld electrodes? I'm not sure about this. How many times we can perform PWHT? Any code reference? So in the PWHT, I don't see any problem if we can do it like 2 or 3 times, but I don't know any reference that suggests a maximum number of heat treatment for P91 or other material.
Generally, these are done for 3 cycles. One during fabrication, one may be any repair in fabrication, and one for the customer for future repair.
Yes.
So generally 3 cycles, and base material and also the well consumed are tested for these 3 cycles.
Yes.
That is the general practice.
This is the practice, but is there any code reference for specifying a maximum cycles? So
no, code will be silent on that. Yeah.
Yes. How long postpone the PWHT activity? There should be no delay for reasons we mentioned earlier, that the delay can. Okay. Sorry. for reasons I mentioned earlier, the delay can result in stress corrosion cracking due to moisture or sulfur species.
The only way around it is if you did post heat or DST, and then you could redo the PWHT. So if you could took it up to 400, and you could stop or pause, but it cannot be for very long.
Yes, it'll be brittle. We should not forget that the hardness is very high in the as welded condition.
Correct.
And it is prone to
Spring cracking.
Cracking.
Omar, I have some experience where the entire vessel was, DST done. Okay, and it was kept because they were not getting the furnace to do the PWHT for a quite longer time. So after 2-3 days, when they got the furnace, they were ready to take it. That time they thought it's better to do a MT to check, the quality of the well. To our surprise, there were a lot of small cracks found in the well. So when we analyzed, it was found that it is because of the chlorine, which from the atmosphere it has taken the chlorine, and finally resulted in chloride cracking because the hardness is quite high.
Yes,
so,
yes.
So as recommended, it's best to not postpone PWHT at all.
I just remembered one case happened to me. There was a coil of P91 material we cut to do the repair, and in order to we cut the main headers, the outlet and inlet headers, and we send it for repair outside, and there was a hydro test required after the repair. So we had to install blinds, and those blinds they brought carbon steel blinds. So so the vendor did not have a WPS for joining carbon steel to P91 material. So they thought it's okay. This is only a matter of hydro test. We can weld this header to a carbon steel and do the hydro test and then cut it again. So we should be careful in situation like this. And vendors are sometimes irresponsible or careless or ignorant about the criticality of this material. Of course, I did not allow them to use this carbon steel material, and we should not allow such dissimilar joints between P91 or.
And for my experience says that for handling this material, you need to have qualified people. It is not everyone's.
Dr. Krishan, you're absolutely right. In the past, if you find the failures after 2005 is more than before. So this is mainly because of the low bidders.
Yeah,
so in the beginning, there was only qualified people to handle such material. But now anyone can come and say that I'm competent and qualified to weld this.
What people do is they just Google it. They get some instructions. They just follow that. They think that is the Bible, which is not actually the case with this material. So this needs to be handled with care. Any ignorance will result in problem.
Yes, ignorance from both sides, from the vendor side and the owner side.
Correct.
We should have knowledgeable people and qualified people in supervising the activities and doing the welding. PWHT is a very critical thing. Sometimes the repair organization involved for such critical repair will subcontract the PWHT to another company. And we know nothing about the qualification of that subcontractor. Yeah. So it's not, it's always the case. you give this job to a qualified repair organization, but from their side, they subcontract the PWHT to another vendor, and you are not involved.
Correct.
You are not aware. So this should be carefully reviewed, carefully witnessed outside by qualified and knowledgeable people during post-weld heat treatment. Any mistake can result in a catastrophic failure.
Yeah, most of the things are irreversible here. No,
we have also experienced that due to this good control required, induction heating is also a preferred method for P91, where control over heating is much better than the different previous ones, where flame is absolutely not recommended. But between the electrical and induction, preference goes to induction for P91 usually because of the better control.
That awareness is missing.
Yeah, I think we've done quite a few jobs since the last 10 years on PWHT for P91 and preheating using induction. And now we've got also a multi-zone induction heater for heavy wall thicknesses, where you can actually, like Mr. Omar said, if you have a heavy wall, dissimilar thicknesses, you can put different zones on it and control different temperatures, so that you get a very good gradual heating zone and very good control on the soaking band.
Yes.
So the awareness is increasing slowly, but it needs to be much more for sure in terms of P91. It's a difficult to handle material.
I think lots and lots of questions are pouring.
Yeah.
Stay away. Yeah, my advice always to stay away from low bidders for P91 material.
Yeah.
Make sure you have qualified people, qualified vendors having good experience in P91 material. It's not just another low alloy grade. It's a different material.
Yeah, you put it very nicely. Yeah.
And again, I'm at the end. I'm sorry, but I'm not active on social media at all. And recently, I saw that there are many platforms for knowledge share, and one of the best platforms I found is yours actually, and you guys are doing a great job, and it's an honor for me to be part of your family, and thank you very much for this.
Thank you so much for accepting our invite once again, and we are sure we are going to come back to you again with another new topic in the coming days.
Yes. And I think it's because of speakers like you that this has been a rich sharing experience for all participants, and it's been really well accepted, and a lot of people have benefited by the knowledge sharing.
Thank you very much. Thank you again.
On behalf of IAW and personally, we thank you.
Yeah.
For this wonderful webinar.
Thank you so much, Mr. Omar. Thank you. We close it here. Further questions, if there are any, please send it to us by email and we'll try to respond to you. You can send it at iawmumbai01@gmail.com or either to Dr. Krishnan or to me. Also, if you're around, do connect with us on LinkedIn so that if there is any questions, you can pop up and we can take it further from there. All right. So on a closing note, a warm thanks to all participants. Mr. Omar, I think we had more than about 130 people during the peak time of the lecture, and good set of questions which were asked and a good Q&A session all around. So once again, thank you everybody for being here on the Saturday evening and doing this wonderful talk.
Thank you very much.
Thank you everybody. Thank you so much.
Bye.
Thank you.
Have a good weekend. Bye.
Have a good weekend. Bye-bye. Bye-bye.
Same to you. Bye.